Welcome to AI Frontiers. Today's journey explores a 24-hour snapshot of AI innovation, analyzing 97 papers from the arXiv preprint server's computer science learning category. This episode reveals the themes, breakthroughs, and future directions shaping our world through the lens of December 5, 2025. Today's expedition navigates the research landscape from theory to application. First, the field of computer science learning will be mapped. Next, 4 dominant research themes emerging from the papers will be explored. Then, shocking findings that challenge conventional wisdom will be examined. Common methodologies and tools of the trade will be analyzed. Finally, a deep dive into 3 landmark papers will be taken, followed by a look into the future. Computer science learning serves as the engine of modern AI. This field focuses on algorithms that learn patterns from data. Unlike traditional programming with rigid rules, machine learning creates adaptable systems. It's the foundation for medical diagnosis, language models, and climate prediction. The December 5th papers show a field maturing but not settling. Research expands in 3 directions: theory, scale, and real-world application. Theme 1 is the Great Compression, doing more with less in AI's efficiency revolution. Economic and physical limits drive radical efficiency improvements. BitStopper introduces transformers that skip unimportant calculations. Quantization techniques shrink models by 68% for mobile execution. KQSVD compresses memory caches without losing conversational fidelity. The future holds full AI intelligence in your pocket, car, and home. Theme 2 is the quest for robustness, building AIs that work in the real world, not just the lab. Lab success doesn't guarantee real-world reliability. Learning invariant graph representations ignores spurious patterns. The paper On the Bayes Inconsistency of Disagreement Discrepancy Surrogates reveals flaws in popular failure detection methods. Researchers provide theoretical fixes for these fundamental problems. The goal is trustworthy AI that handles unexpected situations gracefully. Theme 3 is AI for the scientific frontier. From cat pictures to protein folding, AI earns its PhD. Advanced learning techniques tackle structured scientific domains. Hierarchical geometric deep learning simulates 1,000-atom protein complexes. Physics-informed neural networks predict Alzheimer's disease progression. AI blends patient data with physical principles for personalized medicine. This represents AI's transition from toy problems to grand challenges. Theme 4 is the architecture of thought itself, rethinking how learning systems are built and how they work. Beneath applications, a quiet revolution in foundational understanding occurs. Deep Manifold Part 2 offers a geometric theory of neural networks. QLLSTM redesigns classic memory networks for efficiency and stability. Researchers view networks as systems constructing stable understanding. This foundation work ensures our building tools are sound and well understood. Key Finding 1. Reasoning without massive pre-training. A tiny model challenges the bigger is better paradigm. Compress ARC solves 20% of difficult. ARC-AGI puzzles with just 76,000 parameters. That's over 1,000 times smaller than models like GPT-3. It learns only from the single puzzle in front of it. The model searches for the simplest possible rule to explain patterns. This suggests intelligence may emerge from compression, not just scale. Key Finding 2. The privacy paradox in synthetic data. When fake data whispers real secrets, synthetic data designed to protect privacy may leak information. Querying generative models produces clusters that fingerprint individuals. Attackers can infer that someone like this existed in original data. This forces rethinking from preventing copy-paste to defending against inference. Privacy measures must evolve beyond current statistical guarantees. Key Finding 3. When efficiency undermines security. The dangerous interaction between compression and safety. Model compression can reactivate neutralized backdoors. The Quantization Blindspots paper reveals this critical vulnerability. Backdoor defenses are broken by standard efficiency optimization. This shows optimizing for one goal, efficiency, can undermine another, security. It demands holistic system design, considering multiple objectives. Common methodologies form the AI researcher's toolbox. These are how today's breakthroughs are built. Geometric and dynamical systems theory provides foundational understanding. Physics-informed neural networks combine data with domain knowledge. Novel optimization algorithms like staleness-aware proximal policy approximation are employed. Advanced compression techniques include quantization and sparse attention. Hybrid approaches blend neural, symbolic, and physical computation. Paper 1. Deep Manifold Part 2. Neural Network Mathematics. A unifying theory of everything in deep learning. Ma and colleagues construct a new mathematical language for neural networks. Networks are viewed as geometric systems building stable structures. Learning is active construction, not convergence to existing solutions. The theory predicts single models will fail as geometric complexity increases. It proposes a future of federated systems with smaller, elastic models. Paper 2. A 3PO. Accelerating Asynchronous LLM Training. Pragmatic Engineering for Sustainable AI Alignment. Lee and colleagues tackle an expensive bottleneck in reinforcement learning alignment. The method eliminates a costly extra forward pass in proximal policy optimization. It uses smart interpolation between old and new policies. This achieves an 18% reduction in training time with no performance loss. It makes AI alignment faster, cheaper, and more accessible. Paper 3. Hankel-FNO. Fast Underwater Acoustic Charting. AI is a new scientific instrument. Sun and team create a physics-encoded Fourier neural operator. The mathematical structure of sound propagation is baked into the architecture. It matches traditional solvers, but is orders of magnitude faster. It generalizes better to new ocean regions than data-only approaches. This demonstrates the power of combining deep learning with domain knowledge. Future directions, where AI is heading next. Connecting the dots from today's research. Hybrid intelligences will blend neural, symbolic, and physical computation. Ubiquitous AI will escape data centers into sensors, wearables, and robots. Formal guarantees will provide mathematical assurances for safety and reliability. A great reconceptualization seeks new formulations of intelligence itself. The search continues for paradigms beyond scaling existing architectures. AI synthesis and review. How this presentation was created. Content was synthesized using GPT DeepSeek, specifically the DeepSeek chat model. Text-to-speech synthesis was performed via DeepGram for audio narration. Image generation used Stable Diffusion for visual elements. A human expert reviewed the synthesized content for accuracy and coherence. Note: while reviewed, some oversights may exist. All references are provided. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXivpreprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXivpreprintserver.org.